Welcome to another lecture where we're going to discuss Newton's laws. Last time we went into great detail looking at how to use free body diagrams and be sure that we include all the necessary forces that are acting on an object. However, in the examples that we presented, we constrained our discussion mostly to weight and the normal force. I want to add a few more forces in here for you, actually two more forces, and that is going to be tension and friction. So let's review a little bit of what we discussed before about friction, and let's take the simple case first. Let's suppose that we have an object sliding along a surface. Then when that happens, the friction force will act parallel to the surface and point in the direction that opposes this motion. Okay, so if the object is, for example, moving with a velocity in this direction to the right, then the friction force points to the left. And notice that acceleration is not required for this to occur. A constant velocity will also result in a friction force opposing that motion. It just requires that the object be in motion for this type of friction. The amount of friction is going to be proportional to the normal force through this equation here, where the frictional force is going to equal the frictional coefficient mu times the normal force. And the coefficient mu is something that is either given in the problem and or looked up on a table depending on the surface. It will depend whether you're talking about some rough surface or some smooth surface as to what that coefficient will be. Now, as I mentioned before, this type of friction force is only one of two kinds of friction forces that can exist. Another type of friction force is what will happen when the object actually isn't moving. So these two types of friction force, the one we were just discussing where there is motion, is called kinetic friction. The other type of friction occurs when there is no motion, and that is called static friction. There's a similar formula for static friction, except that it's an inequality, which I'll explain in just a second. But the other thing to take note of is that the mu values are different, even if you're talking about the same substance. For example, wood on wood. The mu k value is going to be different than the mu s value. The other thing about this inequality to keep in mind is that what happens when you're trying to push something, for example, is that the static friction will work to prevent the motion of that object. And it will balance the force that you apply up until you reach this value, mu s n. So for example, maybe I push with a force of 10 newtons on something. Then the static friction, if it's capable of doing so, will oppose that push with a force of 10 newtons. But now let's say I push with 20 newtons. If this normal force times the frictional coefficient can equal 20 newtons, then it will oppose that value with 20 newtons. However, once you reach a certain point, you can exceed this maximum amount of force that can be opposing you, and then you can get the object to move. Once you get it moving, then kinetic friction kicks in, and this value is generally smaller than this value. So you can think about, for example, trying to push a bookcase over a carpeted floor, and at first it's very hard to get it going because static friction is opposing you, but once you exceed that static friction force, then kinetic friction kicks in, and you can keep the bookcase moving a little bit more easily than when you were trying to get it moving to start with. Okay, so let's take an example where we look at, and the other force that I didn't mention yet was tension. We're going to do an example that involves tension, but we're going to look at it both with and without friction. So this example, I want you to think about a sled being pulled across snow. I know that's not exactly a summertime image to have, but this is going to serve as our example for today. In the first case, we're going to look at pulling the sled across the snow, where we can treat the friction between the sled and the snow as being negligible or equal to 0. And if that's the case, we may draw some free body diagram like you see here, where the weight force points down, the normal force points perpendicular to the surface, which is the snow. So we can imagine then that the snow is horizontal. And then the tension force of me pulling on the rope points off at an angle. Based on the lengths of the vectors of these forces, you can deduce what direction the net force is going to be. So go ahead and take a minute to think about that. And after you've thought about it, hopefully you can see that the correct answer here should be to the right. That's the direction of the net force, because if I think about what's going on with these vectors, this tension force has both an x and y component to it. So I can indicate its y component like this, and I can indicate its x component like this. And the tension in the y direction plus the normal force looks to be sufficient to exactly balance the weight so that the sled is not moving up or down, hopping up off of the ground, but there's nothing to oppose the x component of the tension force, and so you've got some net force in the right, to the right. Okay, now a slightly trickier question is, what can we say about the motion of this sled? Take a second to think about it. When you've thought about it for a little while, you might be able to conclude that the first thing you might think is that the sled is clearly moving to the right. Well, that's certainly one possibility. But remember that what the motion is compared to what the force is on the object, this is just a snapshot in time. So, for example, if I throw a ball straight up into the air, when I first release it, the velocity vector is pointing up while the acceleration vector is pointing down. So just because the net force is to the right here doesn't mean that the sled wasn't already moving to the left, right? The sled could have been getting away from me, and now I'm pulling on it towards the right to get it to try and stop or head my direction eventually. So choice B could also be correct. Now, could choice C be correct? Could the sled be stationary? Newton's first and second law tells us that the only situation in which you're going to have a sled be at rest is if there is no net force on that sled. And since there is a net force that we've deduced heading in the rightward direction, then choice C cannot be correct, which means that the correct answer to this multiple choice question is D, both A and B. Okay, now let's consider the same sled, but now instead of the friction being negligible across the snow, we're going to imagine that it's sticky snow in which we cannot ignore the friction. And so there's going to be friction between the sled and the snow. And so to this free body diagram, I've added a frictional force. However, this is a special circumstance that I'm considering. I'm imagining that the sled now has the same acceleration as it did before we added the friction. I'm going to have to do something in order to achieve that, right? If I'm pulling something without friction and achieving a certain acceleration, I must pull somehow harder in order to achieve the same acceleration when there is friction present. So that should help you answer this next question. Whoops. And that is what the tension force is doing now that I have friction. If I am to achieve the same acceleration rate, what has to be true? Well, I've got to increase the tension that I'm pulling the sled with. So that corresponds to choice A here. Now, the next question may not be quite as obvious, so think about it for a second. If the acceleration is unchanged compared to without friction, what does that mean about the normal force between the ground and the sled, or between the snow and the sled pushing up onto the sled? How will that be changed? So I want you to think about that carefully, and if you would like, it's probably good to draw a free body diagram. So when we had, we'll say that this is without friction, and this is with friction. So when we did not have friction, we just had the normal force and the tension force off to this direction and the weight force. Now, assuming that the sled is not jumping up off of the ground, then all the forces in the y direction, when I add them up in the y direction, have to equal to 0. And we looked at that and we agreed that, okay, I think that if you add up this component of the y tension plus the n, it should equal the weight force. Well, what about with friction now? The thing is, I'm not going to draw the normal force quite yet, but the thing is that the weight cannot change, right? It's defined to be mg. But now if I've made this tension vector longer, I have increased not only the x component of the tension, which was required in order to make the acceleration in the x direction be the same, but I've also increased the y direction, the y component of the tension. If I want the sum of the forces in the y direction to equal to 0, then that necessitates that the normal force must be less, right? Because if I have increased the up direction with the tension force, by virtue of the tension force, then I will be risking lifting this up off the ground unless the normal force has decreased. And so the normal force, I expect, if the acceleration is the same, that means it's the same in both directions, i.e. 0 in the y direction, that means that the normal force has to be smaller. Okay, so if that one was a little bit tricky for you, try and see if you can think about why that has to be true. Now that we've done a good bit of drawing free body diagrams using all the different forces that we discussed that you might encounter, tension, friction, weight, and the normal force, I would like to apply some of these concepts to now a problem-solving situation where we first start by analyzing the forces with a free body diagram and then applying Newton's second law in order to solve for a problem. Okay, so we're going to start with essentially a one-dimensional problem. In this problem, we're looking at what we would call an Atwood machine, and you have one object on a pulley with another object. In this case, these are light bulbs. Okay, we're given the mass of each object, which I will call mass 1 and mass 2. And that's basically all we're given. Okay, so we want to know what the acceleration is of these light bulbs. All right, so one thing that you need to know about tension is that when it goes over a pulley like this, remember that I said tension remains undiminished. That's what we're going to assume. So the tension is transmitted through this cord from one light bulb to the other. So the tension for this on this light bulb is going to be the same as this tension. However, we might realize that since this one has a greater mass, I'm going to expect that the acceleration, whatever it's going to be, is going to be down for this one, and since they're connected, it will be the same acceleration that this one goes up with. Okay, so with those two things in mind, let's now draw some free body diagrams. Let's start with mass 1. So for mass 1, I've got the tension force pointing straight up, and I've got the weight force pointing straight down. And when I apply Newton's second law, I know that the sum of the forces, in this case they are all in the y direction, has to equal m times a. Well, what is this sum? Well, we've got the tension force pointing in the positive y direction, and we've got the weight force pointing in the negative y direction. So I'm going to add in negative mg. Okay, simplifying this, the tension can be thought of as equaling m1 times the quantity a plus g. Okay? So for mass 2, I can draw another free body diagram, which is going to look very, very similar to the first one, except that the tension force will be shorter than the weight force. So when I sum my forces in the y direction for mass 2, I have to account for the fact that the acceleration is in the negative y direction. So this is minus m2a. And when I add in that sum, tension minus m2g equal to m2a, I see a similar equation, except that I have this, this minus sign here. Okay? Now, oftentimes with Newton's laws problems, the trick is to take some information that you know about one object or one direction and substitute it into another equation. Oftentimes then it's just an act of however many unknowns you have and however many equations you have. In this case, there are 2 equations and 2 unknowns. I have no prior knowledge of the tension nor the acceleration. The acceleration is what I'm solving for. However, I have this expression I can use from mass 1 to eliminate this tension in this equation right here. So I'm going to substitute for tension from this first equation into the second equation. And I'm going to say then that m1 times a plus g is going to equal m2 times g minus a. Okay, I will leave you go through the algebra and simplify all of this. We need to isolate the a and get that all on the same side of the equation. So I'm going to put a dot, dot, dot. You should try your hand at making sure you've got all the algebra sorted out. But in the end, you should be able to find this expression. Okay, when you've done that, now you're in a situation where you can plug in the numbers because we know what G is, it's 9.8. We know what M1 is, that was given to us, as was M2. And when you punch that into the calculator, you should find an acceleration rate of 1.96 meters per second squared. Okay, so in this example, we thought about free body diagram for 2 different objects, and we thought about how to apply Newton's second law to each of those objects, and then we utilized the equations that came out of applying Newton's second law in order to deduce the quantity that we needed by solving a system of 2 equations and 2 unknowns for the unknown that we were looking for. Okay, so this is the typical way you're going to go about Newton's laws problems. In the next lecture, we will do a little bit more complicated examples, and I will talk to you more then.